In this lecture, we'll continue with Chapter 5, Section 3 on relationships between two quantitative variables and linear regression. We'll talk more about the equation of the regression line and computing residuals. We'll talk about the effect of changing the roles of the explanatory and response variables. We'll talk about what it means for an observation to be unusual. We'll talk about looking at a sample versus the population when we're doing regression. And we'll talk briefly about time series and look at additional variables. In the 4 stages of statistics, we are still talking about displaying and summarizing two quantitative variables. In the last video, we talked about using a scatter plot to display a relationship between two quantitative variables, and to summarize the relationship with the form, either linear or curved, the direction, positive or negative, the strength, strong, moderate, or weak. If we're looking at a linear correlation, the correlation coefficient R gives us both the direction and the strength. Also, if it's linear, the equation of the regression line gives us a way to predict a y value based on a given x value. The regression line, or the least squares line, allows us to summarize a linear relationship between explanatory and response values. We use x for the value of the explanatory variable and y hat for the predicted y value. The error in the prediction, that is the actual value minus the predicted value, or y minus y hat, is called the residual. Let's look more closely at the numbers involved here. The slope of the regression line is how much we expect y to change by whenever we increase x by 1. The intercept is where the best fit line, the regression line, crosses the y-axis. In your algebra class, you probably talked about the y-intercept being the value of y when x is 0. We have to be careful about using that interpretation here, though, because x equals 0 might not be a valid choice. Let's take a look at an example. The regression equation for price of a used Grand Am given the age is here. Price is equal to 14,690 minus 1,288 times the age. What can we learn from the slope and the intercept? How do we interpret them? Remember, the slope is the rise over the run of the line. So if we increase the x value, that is the age, by 1, we expect the y to change by whatever the slope is. So the slope of negative 1,288 is how much the price will drop for each 1 year increase in the age. The intercept we interpret as the place where the line crosses the y-axis. We should be careful, though, about saying that the place where the line crosses the x-axis is our prediction for when the age is 0. Just because the line predicts that the price of a 0-year-old Grand Am is $14,690, that does not mean that we predict that a new Grand Am costs $14,690. The reason is we used used cars to get that regression equation. All of the ages were greater than 0. Going back to an age of 0 would be extrapolation. Remember, extrapolation is using the regression line to predict a y value for an x value that's outside the range of x's we used to generate the line. In general, extrapolation leads to very bad predictions. For example, if we create a regression line based on male students' weights and heights, we get the equation y hat, that's the predicted weight, is equal to negative 438 plus 8.7x, where x is the height in inches. What weight does the line predict for a 20-inch long newborn? Well, plug in 20 for x, and you get negative 264 pounds, which is clearly not right. Since the regression was made using male students, we can only use a range of values for x to create predictions that are within that range of male students. Newborns are generally not students. Let's look a little more closely at the slope and the intercept. Remember that we use b naught, that is b sub 0, as their notation to indicate the intercept of the regression equation, and b sub 1, or just b1, that represents the slope. Now, the slope, b1, can be computed as r, that's the correlation coefficient, times the standard deviation of y, which we see here in the numerator, divided by the standard deviation of x. This kind of makes sense because, remember, slope is computed as change in y over change in x. So that means that we interpret the slope b1 as if x goes up by 1 standard deviation, in other words, we increase the denominator of that fraction by 1, we would expect y to go up by the numerator of this fraction, which, if you think about the r as r over 1, then the numerator of the fraction is r times the standard deviation of y. So if x goes up by 1 standard deviation, y should go up by r standard deviations. And remember, r is a number between -1 and +1. So that means that y will either go up by 1 full standard deviation or less, or it could go down by 1 full standard deviation or less. If the absolute value of r is close to 1, that means y responds very sympathetically with x. If x goes up by 1 standard deviation, y will either go up or down, depending on the sign of r, by nearly 1 standard deviation. If r is close to 0, increasing x by 1 standard deviation results in a very tiny change in y. So a meaningful change in x gives us barely any change in y. That means that y does not respond well to x. Now the computation for the intercept is b0 is equal to y bar minus b1 times x bar. Remember, b1 is the slope. So if we plug in x equals x bar, what y would we get as our prediction? So if we plug in the mean for x, what do we get for y? Well, y hat, that's the predicted y we see here. This is the equation of our line, b0 plus b1 times x bar. Now let's substitute that computation for the intercept in for b0, y bar minus b1 times x bar. We still have the plus b1 x bar, that's here. And now notice that I have minus b1 x bar and plus b1 x bar. Those cancel out, and I'm left with just y bar. That means when I plug x bar into the regression equation, I always get y bar. If you plug in the mean value of x into the regression equation, you get the mean value for y. That means that our line always passes through what's called the point of averages. The x value is the mean x, the y value is the mean y. Remember, we defined the residual of a data point. So we already have a point on our scatter plot. The residual of that point is the vertical distance that point is from the regression line. In other words, it's the difference between the observed y value, the actual y value of our point, and the predicted y value, that's y hat, that we get from the regression line. In other words, it's the observed value, that's yi, minus the predicted value, that's yi with a hat on it. So the residual for the first data point is indicated with maybe x1 comma y1. We plug in the x1 into the regression equation, and we get y1 hat equals b0 plus b1 times x1. We subtract y1 minus y1 hat to get the first residual. If we do that for all of our data points, we can use that to find S. That S is called the standard error for the regression, and it's the residuals squared added together divided by n minus 2, and then we extract the square root. So you can think of it as a way to sort of find the average residual. That's why it represents that typical residual size. Let's talk more about using Excel to do regression. Here you see some data for high temperatures in Spartanburg and in Charlotte over the first part of this month. I would expect that hotter days in Spartanburg would lead to hotter days in Charlotte. So I think there would be a pretty strong relationship between these two. I've already shown you how to use the data to create a scatter plot and use the scatter plot to get the regression line. I'm going to show you how to do it without the scatter plot now. There are 4 formulas that we'll need to use. The first is one that we'll use to find the correlation. That's R. The second one we'll use to find the slope of the regression line. The third will find the intercept. And the fourth will find the standard error. Let's start with the correlation. To find the correlation, you can go into Formulas, More Functions, Statistical. The one for correlation looks a whole lot like correlation. It's C-O-R-R-E-L. Notice that correlation just asks for 2 arrays. It doesn't say which one is X and which one's Y, because remember, interchanging the X's and the Y's does not change the correlation coefficient. So for array 1, I'm going to pick the Spartanburg numbers. For array 2, I'm going to click in array 2 here, and I'm going to pick the Charlotte numbers. And I'll click OK. The correlation here is 0.9. That's pretty strong. Now let's find the slope of our regression equation. That's also under our statistical functions. And you're looking for just what you would expect it to be, slope. Here, the y's and the x's matter. So we need to start by entering the known y values. I'm using the Charlotte temperatures as my y values, so I'll put those in first. And then for the known x's, I'll choose the Spartanburg values. When I click OK, that gives me a slope of 0.8735016. Now for the y-intercept, again under More Functions and Statistical, it's intercept. Again, we enter the y's first, and then the x's, and click OK. The y-intercept is 12. The standard error is a function that's a little bit harder to find. It doesn't quite look as much like you would expect, but it does kind of look like standard error. It's STEYX. The ST for standard, the E for error, and then Y's and X's. Again, we enter the Y's. So I'm selecting all the Charlotte data, and then the known X's. And that gives us a standard error of 1.8450, etc., etc. Remember that standard error tells us the typical size of a residual. I can compute all the residuals in the following way. Remember, the residuals are the observed Y value minus the expected Y value. To get the expected Y value, we will take, well, let's do this in a couple of extra steps. I want to insert a column. Here's our expected Y value. The expected Y value is, this is going to be a formula, so equals, it's the slope, 0.8735016, times the X value, so I'm clicking on the right X value for our expected value, plus the intercept, which is 12.0435016. So there's our expected high temperature. I'm going to fill down to copy and paste that formula into all of these, and there's all of our expected values. The residual, remember, is equal to the observed value minus the expected value. So our first residual is negative 0.78, and here are the rest. I see residuals as big as 4 in absolute value. There's a 3, another one close to 4. But overall, if you look at those first digits, they tend to be zeros and ones. The standard error was 1.84, so that means the typical residual will be within 1.84 of 0. And sure enough, that's what we see more often than not. Now let's do something similar on our calculators. Here I've entered the same data into L1 and L2. If you want to follow along with your calculator, go ahead and pause the video, take a look at the numbers on the left of your screen. You see the data that we're using, and enter the Spartanburg numbers into L1 and the Spartanburg and the Charlotte numbers into L2. Once you've got those in, I'll tell you how to find the standard error. To find the standard error, we go to Stat, and here we want to go over to Tests. Now we're looking for one of the tests that involves regression. It's actually easier to go up than down here because it's at the very bottom of this list. We're looking for linear regression t-test. It's option F on this calculator. It may be different on yours. But look for that linear regression t-test and enter. Now your X list should be L1, and ours is, so I'm going to push down to go to the next one. The Y list should be L2, and it is. The frequency we want is 1. What comes next here is something that we don't need to worry about right now, so just go ahead and push down again to skip that. Next to regression equation, if you would like for this to automatically paste the formula into, let's say, Y1, you can do that here by choosing Y1 out of your variables menu. I'm not going to worry about that, so I'm going to go on down to calculate, and I'll push enter. Now here we get the regression equation, y equals a plus bx. A is the intercept and b is the slope. We can skip all the stuff in the intermediary for now, but you see A, that's the intercept, B is the slope, and S is the standard error. And you may notice that's the same as the standard error we got before, that 1.845. That's good news for us. Now what if we actually wanted to check the residuals? You could compute them all by hand using your calculator, but there actually is an easier way. Go back to your Stat menu and edit. I want to put the residuals in, let's say, one of these other lists in one of the L's. So what I'm actually going to do is in L3, I'm going to put our predicted values, which is what we did on Excel a moment ago. And the way I'm going to do that quickly and easily is I'm just going to enter a formula for L3 in terms of L1 and L2. Remember, A was our intercept and B was our slope earlier. So I want L3 to be equal to the slope. And I can find the slope by going into Variables, Statistics, Equation, and there we see A and B. Remember, A was the intercept and B was the slope. So I want the slope first. So I want the slope times the number in L1. Notice that you've got an L1 above your 1 key, so I'll hit second L1. And now I want to add the intercept. Remember, the intercept was A, so I'm going to go back into Variables, Statistics, Equation, and I'll choose option 3 to get B. Whoops, I don't want B, I want A. So I'm going to go back, I want to delete that. Variables, Statistics, Equation, and I'll choose option 2 for A. And then when I push enter, notice that fills in all those expected values. See how they match up with what we had before? Now in L4, if I push arrow over, I can see L4, I can compute the residuals. To put in the formula, I'm going to go up and highlight L4. The residual is the observed value, the actual value, minus the expected. So this should be L2 minus L3. And there we have our residuals. Let's look at our grand AMs again. Let's say the first two data points that were used to get the regression equation were 4 13,000. So some grand AM out there that's 4 years old costs $13,000, 8 4,000, and so forth. The regression equation is 14,686 minus 1,290 times the age. And our software reports that S equals 2,175, R squared is 78.5, and R squared adjusted is 76.7. You don't need to worry about that adjusted R squared. So what does the 2,175 mean? Well, again, we interpret that standard error S as the typical size of a residual. Obviously, that one line can't go through every single data point. So, for example, the first data point, 4, 13,000, when you plug 4 in from that first point into the age, you get a prediction out of y hat equals 9,526. The actual cost was 13,000, so the prediction error is the difference in those, 3,474. Positive because the actual value was higher. If the age equals 8, we plug that in. X equals 8 gives us y hat equals 4,366, whereas the actual observed value is 4,000. The observed value is below the predicted value, so the difference, observed minus predicted, gives us a negative number, negative 366. The way we interpret S, the standard error, is that if you look at all of the points that we use to generate the line, the size of the residuals will be overall typically around $2,175. Of course, that means some will be higher and some will be lower, but on average, that'll be about the size. Here's a scatter plot along with the graph of the regression line. The residuals are indicated with the vertical red lines. Notice that some have a vertical distance more than 2,175 and some less. Notice also that in the computation for S, the difference between the actual value and the observed value gets squared. That means that the distance, whether the point is above or below, does not matter in this computation. when we talk about this error, we're thinking of it as positive, even if the point is above the line or below the line. Here's another couple of examples. Here our individuals are schools, and in the first plot we have math SAT average on the y-axis, so it's the response variable, and average verbal SAT score on the x-axis, so it's explanatory. Second, we have the average math SAT, again the same set for the y's, but here for the x's, for the explanatory variables, we have the percentage of teachers with advanced degrees. Notice that if you look carefully, you can see that every point on the left, like this highest one, lines up exactly with one of the points on the right. So this is the same set of schools. So how do we interpret S for these? They were each given to us. On the left, S is 7.08, and on the right, S is 26.23. Notice that on the left, the correlation, R, is positive 0.97. That's really, really strong. It's close to positive 1. That means the typical error will be really small. 7.08, when you're talking about math SAT scores, is not much at all. On the other hand, the 26.2 is the typical residual size for the other regression. Since R is positive 0.41, which is not very strong, we expect the residuals to be greater because the y values do not depend as much on the x values. Remember, if you're only given r squared, you can find r by taking the square root and choosing the appropriate sign. Here are two examples. The first shows a relationship between price per kilogram and price per pound for groceries. We expect those to line up perfectly. And students' final exam score versus the order it's handed in. One of these has an S value of 0. The other has an S value close to the standard deviation for the y's. Of course, the one on the left is the one with S equals 0. We can perfectly predict the price per kilogram based on the price per pound. The one on the right, however, has S close to the standard deviation for y. The reason for that is the regression line is approximately horizontal, and remember, it goes through the point of averages. So the residual for each point is essentially the distance the y value is from the mean y, since the regression line indicates the mean y. Therefore, the typical residual is about the same as the typical distance of a y value from its mean. That's exactly how we interpret the standard deviation of the y's. We mentioned in the last video that the choice of explanatory or response when you're considering the two variables does not affect the value of the correlation. So R will be the same either way, no matter which data set you choose for X and which you choose for Y. However, that does not mean they'll have the same regression line. Here we have 4 given points. On the left, we're putting the y's on the x's. In other words, we're using the y's as the y variables and the x as the x variables. On the right, we're doing the opposite. We're using those same points, but we're interchanging the x and y. Notice that the lines are different. The one on the left has a very shallow slope, while the one on the right has a steep slope. When we regress y on x, we get that slight negative slope. We're trying to minimize the prediction errors of predicting the y value based on the x value, so those are vertical. On the right, we saw the same points plotted, but we're trying to minimize the prediction errors horizontally. That gives us that steep negative slope. So remember, when you're trying to find a relationship between two quantitative variables, consider the context. It's important. Decide which one you think should depend on the other, and assign the roles accordingly. When we're talking about an outlier in a regression, we're talking about a data point in the scatter plot with a really strangely large residual. Here, the unusually large we measure with respect to the standard error. An influential observation is one which may not have a big residual, but one which affects the regression line very strongly. Let's look at some examples. Take a look at this scatter plot, which shows on the horizontal axis an explanatory variable of fleet size for several smaller airlines. On the vertical axis, we have the response variable, which is orders for new planes. If you draw a loop around the data points, the cloud generally looks like this, and we can draw in the line that fits in between them. Now, look at Southwest and JetBlue. Are each of these an outlier? Is it an influential observation? Let's look at Southwest first. It is very much an influential observation. The reason why is if you pretend like it's not there, our new cloud of points looks like this, and that really changes the line. We can also see that it's not terribly far away from the regression line, which means its residual is not very big. That makes it not an outlier. JetBlue, on the other hand, is an outlier. It has a very big residual. If you drop it and look at just the points that remain, R goes up by quite a bit, from 0.69 to 0.97. As we move from a sample to a population, we can talk about the slope of the regression line in the population. Instead of using B1, we'll follow our previous convention and change that to beta 1. Similarly, we'll indicate the intercept of the regression within the population using beta naught or beta sub 0. It's not unusual for us to use Greek letters to refer to parameters out of the population and regular Latin letters to refer to samples. So, if we have a scatter plot based on data taken from a sample, we talk about the predicted response, y hat, equals b naught plus b1 times x. If we're looking at the line that best fits all of the points in the population, then we call it the mean response, not the predicted response. The mean response is mu y. Remember, the mean in the population is mu, so the mean response we'll call mu sub y, equals beta naught plus beta 1 times x. And remember, the larger the sample is, the closer we are to the population, the more evidence we have of a relationship. Let's talk a little more about sample size. Here we see scatter plots for to display the relationship between ages of students' mothers and fathers. Now it happens that both scatter plots have the same correlation coefficient, 0.78. On the left, the sample size is over 400. On the right, the sample size is 5. Which of these provides more evidence of a strong positive relationship in the population? Well, it's the one on the left, that larger N. I know we've said over and over again that the bigger the sample is, the more evidence we have for whatever relationship we see. But even just looking at the scatter plots, the one on the left looks like a stronger cluster around a line than the one on the right. Even though the correlation coefficients are exactly the same, the strength of the relationship is the same, but the one on the left just looks better. The one on the right looks like it could have arisen just from chance. One last thing we'll look at is the notion of a time series. When we're looking at a relationship between two quantitative variables, and the explanatory variable is time, we'll sometimes call this data set a time series. To evaluate a time series, plot the points and connect the dots to see if you can identify a general trend, or also identify peaks and troughs in the graph. For example, this time series plot shows average daily births each month in the year 2000 in the United States. Do you see a peak and a trough? Certainly there's a trough in April, which happens to be 9 months after July. So we might infer that fewer conceptions occur in July. And there's a peak around August and September, which is 9 months after the December holidays. So conceptions are up at that time of year. Finally, let's look at the effect of confounding variables. If we have two different groups that are combined to create a regression, it can really affect the nature of the relationship that we see. More advanced techniques in statistics will take a look at more than one explanatory variable. This is called multiple regression, but we won't have time to talk about it in this class. Here's an example. Here's a scatter plot for phone time in minutes the day before and weight. This comes from the student survey data. We see that there's a slight negative relationship. Does this mean that heavy people talk on the phone less, or that skinny people talk more? It's possible that gender is a confounding variable. Men overall tend to weigh more than women, and women overall tend to talk on the phone more. Maybe. I know that's a generalization. If we look at males and females separately, so if we block our sample so that we have males, which roughly fall in the circle that's blue on the left, and females, which fall roughly in the circle in red on the left, notice that for the males and the females, there's very little strong relationship. In fact, both of them tend to be more or less positive. Here's another example of Simpson's paradox, where overall there's a negative relationship, but within each of those two subpopulations, there's a positive relationship. Here's a quick example of multiple regression. We've already seen using a car's age to predict its price. What else might be a factor on the price? Well, if you've ever shopped for used cars, you know that the longer a car has been driven, the more miles are on the odometer, the cheaper it will be. There are other possibilities, including maybe previous owners, whether it has been in an accident, all sorts of things. To get a better model, that is a better equation, to allow us to predict the price, we would hopefully get an equation that takes all of those variables into account. That's what multiple regression does. To wrap up, we considered the equation of the regression line. From that, we looked at the slope and the intercept and how to interpret them. We talked about the dangers of extrapolation. We talked about residuals and how the typical residual size is S, the standard error. We talked about how the actual regression line will change if you switch the explanatory and response variables. We talked about the effect of outliers and influential observations. We talked about the notation that we use for the sample line and the population line, and how sample size can affect our perceptions. We talked about time series, and we talked about the role of confounding variables or adding variables to our regression to get multiple regression.